Right, so let's continue with our program. So the last session of today is the second hands-on session. Elie will be leading this session. He's going to be talking about parser implementation, writing a parser for IPv4 and IPv6. Elie, are you ready?
Yes.
So I will let you share the screen.
Okay. So now in the second part of the hands-on, we will see how we can implement the parser. We will be writing a parser for IPv4 and for IPv6. So going back to the original figure that shows the pipeline, we are now working in the first element here, which is the programmable parser. Now, it's a programmable parser. This means that allows you to parse arbitrary headers, and it has a finite state machine. What we need to understand here is that we don't have to we don't have to parse standardized protocols such as IPv4 or Ethernet. We can basically create our own protocols, and because of this programmability of the parser, we can actually parse those protocols. Okay, and this is expressed in a state machine, as we can see here. So we start with a given state, let's say the start state, and then we jump from one state to another. And this jumping here, we call it transition. So how can we define those? We've seen them briefly in our program. Now we will write them again and compile the program and test everything. But the idea here is that a certain protocol has some headers. For example, here we can see we have the IPv4 header. This is how it looks like. So here you have the bit numbers from 0 to 31, and then you have these different fields. So what you typically do is you would define a new header by using the header keyword, and then you give it the name. Here it's IPv4. We add to it _t because we'll be using it as a type to instantiate a new header. And basically, you would start mapping all these fields to their actual representation here in P4. So for example, version starts from bit 0 to 3. So these are 4 bits. So bit 4 version. You have IHL, another 4 bits. So bit 4 IHL. Now, if we look here at this now, we can see that these two fields, the SCP and ECN, can be used for this diff serve. So you have the option to say, I want to make it, let's say, bit 6 the SCP and then bit 2 ECN. Let's say if you are planning to use those separately, you have the option to do so, or you can actually combine them, right? And typically, whatever you parse here, you have the intention of using it later on in your program. And then you have fields such as the total length, identifier, and so on. And then at the end, you have here the source IP, destination IP. Okay, so you can see them here, source IP, destination IP. Now, the IP options, they are optional. They're not included here, but also you have the option to actually parse these options. So how can we write this parser? We have to always start by the starting state, and it's called start. So you define that. You transition from one state to another by using the transition keyword. And then basically you would decide which state you want to go to next based on some fields that you have in the current header. Okay. In this case, we are saying let's look at the ether type value. If it is equal to IPv4, then we go to the parse IPv4 state. Otherwise, we can reject. So the objective of this lab, we will use the exact same topology as the one that we used before. We have one P4 switch and two end hosts. What we will be doing is defining the headers for the Ethernet, the IPv4, and the IPv6. Then we will implement the parser. And later on, when we send the packet, we will be verifying that based on whatever is inside that header, right? If it is IPv4, then the IPv4 state will be executed. If it is IPv6, then the IPv6 state will be executed. Here I added at the end a reference on how these headers look like. So basically, this is what we will be defining in our headers file. All right, so let's move now to the hands-on part. So I already made the reservation. Now we are working on lab number 4, which is called parser implementation. Okay. I will do the same thing. I will undock it, put it aside, and then have the client on the right-hand side. Okay. So as usual, we have few description on what's the lab about, like in the previous lab that we discussed. Now here, because we are talking about the parser, you will see in the intro, we are telling the reader what these headers look like, the Ethernet, the IPv4, and the IPv6. Okay, but again, if you are planning to parse some other kind of header, all you have to do is look at what are the fields that are inside that header. And based on those fields, you will start by writing the header description in your P4 program. Okay, and here we are showing a snippet of this P4 program that has these headers there. And then we go to the programmable parser part and we describe the syntax. But I will not go over them here. We will go over them as we do the lab. So we'll start with the hands-on part in section number 2. So again, we have the same topology. We can see here now that beside the 10.001 and 10.002 IP addresses for host H1 and H2, we have the IPv6 addresses as well. So AAA, and then : 1, and then BBBB : 1. Okay, these are the IPv6 addresses for H1 and H2. Okay, so step 1, as usual, we will start the mini edit graphical user interface, and it's asking us for a password. The password is also here password. All the labs will have the same credentials, so it's gonna be password in all the labs, all small caps. Okay, and then we will load the topology for lab number 4. So this is already built. File, open, lab 4, and lab4.mn. Now that we have the topology there, which again is the same as the one that we used before, all we have to do is start the emulation by clicking on the run button here at the bottom of mini edit. The buttons are grayed out. It means this topology has started successfully. We will do the same starting point from the previous one. So we'll first open the terminal of the host H1, right click, and then terminal. And from there, I will issue a ping from H1 to H2. This is using the ping command. Just to make sure that there's nothing on the switch and we can't forward packets now. And we can see that there's no replies. So the switch is empty. There's nothing, there's no program on the switch yet. Now we will start with defining the headers that we want to parse in our program. Okay. And again, we will use the same environment. So we will go to the desktop and then click on the terminal icon. This is step number 1. And then step number 2 would be to launch the Visual Studio Code and pass to it as parameter the location of this specific lab, which is lab 4. Okay, so now we are inside the environment. We have also the same files, but we will check now the headers.p4 file, and we will see that it's empty. It only has few comments here. Our job in this lab is to actually fill this file here. Okay, so the first thing that we start with here in this headers.p4 file, we'll start by adding some type defs and some constants. Specifically, we're going to add type def for the MAC address to be 48 and for the IPv4 address to be 32 bits. And these are type defs, so you can use bit 48, or you can just simply use MAC address _t for better readability of your program. And then you would have like a constant here, type _ IPv4, that has the value 800 in hexadecimal, or 800 in hexadecimal. Okay, so I will type these under the first command. Type def bit 48, then MAC address _t, then another type def for now the IPv4 address, so IP4 address _t, and then we will create this constant 16-bit, so const bit 16. The name is type _IPv4, and the value is 0x800. Okay. Now, step number 3, we will start by defining the header for the Ethernet. Okay, so we will do that under the Ethernet header command here, and I will be typing this header definition here, and basically this corresponds to the figure that we were looking at in the slides, right? So you have the destination MAC address, the source MAC address, and ether type. So you have to write them in that order. So header Ethernet _t, and inside it we have MAC address. This is going to be our destination MAC, so the ST address. You can obviously call them whatever you want. You are not like forced to use the ST address. You can use destination MAC or whatever name you want to give to it. And then source address. So after these addresses, we have the ether type, which is 16 bits, so bit 16, and ether type. Okay. Next, we will define the header in step number 4 for IPv4. Okay, and we will do that below the IPv4 header. So it can be a little bit tedious to write all the stuff here. Typically, what you would notice whenever you start experimenting more and more with P4, you would have all these IPv4, Ethernet, IPv6, all of them will be already available. You just copy them and use them. But the nice thing about the programmability of the parser is that you can define your own header and your own protocol. You know, and so that's why here we are defining everything from scratch, because for a P4 switch, it doesn't understand what IPv4 is, right? You have to tell it what the IPv4 header looks like. You are instructing it everything. Like you have to assume that it doesn't know any of these protocols, Ethernet, IPv4, MPLS, or any of those. All right, so let us now type in the following for defining the IPv4 header. So header IPv4 underscore T. And then we have 4 bits for the version. We have another 4 bits for IHL, the header lengths. And then we have 8 bits for the diff serve, 16 bits for the total length, another 16 bits for identification, 3 bits for the flags, 13 bits for fragment offset, and then you have 8 bits for the time to live, TTL, another 8 bits for the protocol. This is gonna tell us if you have TCP or UDP in the next layer. And then you have 16 bits for the header checksum. And finally, you have the IPv4 addresses. So we will use now the type def IPv4 address T, and then source address. And then we will use it again, but now for the destination address. For at this point, we are not planning to parse IP options. IP options can be a little bit complex to parse because it can have like a variable length. Hopefully, we will be doing that in the future libraries. Okay. So now we define the Ethernet, the IPv4. Next, we will create a struct for our metadata, but we will keep it for now empty. So I will write here below the metadata struct. So struct metadata. You can leave it empty. You can type in a comment here, empty, obviously. And then, most importantly, we have to group those headers that we intend to use. And we have to first instantiate those headers and group them into one struct, which we call headers here. So struct headers. And here we have Ethernet. So note how we are using here the underscore T, because this is how we defined what the type is like, this header. And we are creating an instance of it, which is this Ethernet here. And then IPv4 underscore T, and then IPv4. So now that we've done with this file, we have to make sure to save it by pressing on Control S or File and then Save. Next, we move to the parser implementation, which should be written inside the parse.p4. Again, I just want to make it clear that you can actually write all the stuff, or everything that you are doing now, the headers, the parser, the ingress, egress, everything inside one file, the basic.p4, and it works well. But we just separated it for better visibility, and so that for first-time learners, they just go to the specific file and know what they are doing instead of having a very large file to deal with. Okay, so step one, we have to click on parser.p4. And basically, you can see that we already have here my parser there. The reason we already have it because it's kind of like a, most of the time it's going to be the same thing. So we will not modify any of those. And the reason is because the V1 model expects you to pass an instance of this parser here that has exactly these parameters, right? So in case you want to modify something, you might want to modify the names. For example, instead of HTR, give it a different name. But there's no reason to do it, at least at this point. Okay, So we will start first by our first state, which is the start state. This is where the parser begins execution. I will add here state start. And when we type in a transition and we give another state here, for example, parse Ethernet. So what happens is that I'm doing a non-conditional transition. So I'm not making any kind of conditioning here before we go to the parse Ethernet state. Okay, so I'm telling it as soon as you start parsing, go to a state that's called parse Ethernet. Now, where's that parse Ethernet state? You have to write it. Typically, it's a good idea to create a state for each of the headers that you are parsing. This is like a common practice, although not necessarily required to do it like this, but it's better so that you have everything separated. So now we will implement the parse Ethernet state. So I will write that below the command for the parse Ethernet. And this is gonna be state parse underscore Ethernet. And within that state, first we have to extract the headers, right? So this is done by using the extract method, which is provided with the extern packet. So packet.extract, and you specify here what are the headers that you are planning to extract. So if you write here, for example, header.ethernet, what happens is that the compiler will look at how big this Ethernet header is, and it can know that because we already defined the header. We specified, let's say, 48-bit for the destination, 48-bit for the source, and 16-bit for the ether type. So it knows how big that is. And you can think of it like a cursor, right? So start taking all these bits and then put it inside the header.ethernet so that you can use it later on in your program. So now that we have this header Ethernet extracted, we can inspect the ether type to determine what is the next protocol, whether it was IPv4 or IPv6 or any other protocol. Now, to do this, we're going to do a transition, but this time it should be a conditional transition. So we do this by using transition, and then we use a select statement. The select statement kind of have like a similar syntax to what you would write in a C language when you use switch, right? But the difference is you don't have break or anything like that. The idea here is very simple. I want to transition by after I only do the transition after checking for whatever you write inside this select here. So in our case, we were gonna look at the header.ethernet.ether type. Okay, so we wanna do the transition, but only after looking at the value of ether type, which is found inside my Ethernet header. Now, if this value, so if the ether type is equal to type IPv4, which we defined in the headers, right? 0x800, then we will go to a state called parse IPv4. Otherwise, so we have a default here. Default means if none of the previous conditions matched, we will just accept. It means I only parse Ethernet and then I accepted the packet. Okay. Now, we said here that we're going to go to the parse IPv4, but there's no parse IPv4 yet, so we have to define it. Okay, and this is step number 4. It's going to be here under the add the IPv4 state below. So state parse IPv4. And here we will also do the extraction, but this time this is going to be for header.IPv4. And again, I can use those here, IPv4 and Ethernet, because this is what I combined in my structure header, right? In the struct that I created, we have Ethernet and we have IPv4. So that's why I'm able to using them here. And here, I will just do a non-conditional transition to accept. Okay, The next step would be to save the changes by using Control S or File Save. Now we can test the program. Hopefully we didn't do any typo because we wrote a lot of small stuff. So P4C, basic.p4. Basically, you have a lot of files here, but you only need to compile the main one, right? And because that main one is including all the other files, then everything will be taken care of. So it compiled successfully. We have an output, basic.json. This is going to be used for our switch. And as we did in the previous lab, after having this compilation successful, we need to push this output to our switch S1. And we will do so by using the push to switch script. We give it the file name, basic.json, and the script and the switch name, which is S1. It's asking us for a password. The password is password, all small caps.
So Elie, before you continue, just to highlight a few things that are pretty cool about P4 is that the switch is not aware of any protocol that's protocol independent, and you had to write IPv4 Ethernet. But the other thing is that there is nothing preventing you to keep parsing or build your own protocol or parse, let's say TCP or UDP. What are the limits when you work with these devices?
Yeah, so at the end, you can do as much parsing as the resources allow you, right? Typically, when you work on a software switch, you don't have that limitation. It's not a big problem, especially for this BMV2, because BMV2 at the end is a software switch. It doesn't matter much how much you can go deep inside the packet. But when you work with a hardware switch, for example, in Tofino, there you have some limits on how much you can go inside the header, how many bits you want to extract there. And the nice thing about Tofino, if you want to work with the hardware, is that their software version, which is the Tofino model, would be exactly the same thing as the compiler for the hardware. In other words, if you have an error complaining that you have some issue with the parsing, or you have some issue in anywhere in your program, then this is the same error that you will get on the hardware. But if it's accepted by the model, it means that, okay, it's now going to work on the hardware. Now, how much we can parse, it depends on the architecture. And I mean, we can't give specific numbers, right? But I would say you can go a little bit. I mean, you can, a lot of applications, they parse TCP, and you can parse a little bit higher than that as well without any implications on the performance. All right. So now that we pushed our output from the compiler to the switch S1, we can proceed to verify the configuration as we did before. So this is going to be step number 5.2. So we will go back to our mini edit by clicking on the mini edit item here. And then we will go inside the P4 switch, inside the file system, by right-clicking and then hold the right-click and then terminal. So make sure to hold the right-click, because sometimes you issue a right-click and then it just pops up and disappears. So make sure always to hold it so that you can get through and launch that terminal. Again, we're going to make sure that our output is the compiler's output was pushed successfully. So we will use ls, which shows the current files, or the files inside a certain directory. In this case, the current directory. You can see we have basic.json. Then we can use the command ifconfig also to see the interfaces as we did before. And we can see that we are using the same topology. So we also have S1 ETH0, S1 ETH1. Now, when you create your own topology, you might have, let's say 2 P4 switches, 1 legacy switch, you might have an open flow switch. So you would see that the number of these interfaces will increase. It depends on how many links you have out of your switch. And I just want to mention that, especially like if you're interested in building your own topology, if you want to know which one of these interfaces correspond to which side of your switch or which link of your switch, you can go to the Mininet terminal, and this is the terminal that's already there when you launched MiniEdit. So in my case here, it's called shell number 1. And there you can simply type in links. And this is going to tell you that you have host H1, which has the interface H1-ETH0. It's connected to S1-ETH0. So we know now that H1 is connected to S1-ETH0. And then you can see that we have H2 connected to S1-ETH1. So we know now H2 is connected to this interface. And this is very important because when you have a bigger topology, you might have a lot of interfaces and you need to keep track of them so that you can program your data plane correctly. Okay. Next, we will start the daemon as we did before and allocate the interface and enable logging. So I will type in here this command, simple switch -i 0 at S1-ETH0. And then -i 1 at S1-ETH1. Nanolog IPC. And then the program name, which is basic.json. And of course, at the end, we can run it in the background. This is not necessary, but instead of having to open a different terminal for the switch, you can just simply run it in the background and then run another program on the same terminal. Okay. Then going to step number or section number 6.2. Step 1, just press enter to get the terminal back here. And here we are also pushing in step number 2 the table entries to the switch by using the simple switch CLI. There's a lab number 7, that will navigate through the simple switch CLI. We're going to do that next week. And this is going to show you all the steps you need so that you populate the tables manually. Okay, for now, we're just going to use a script that already has the rules. So this is lab 4 and rules.cmd.
Elie, there is one question, perhaps is a good point to answer this question because it's related to what you just said. How can we push the output of the compiler to the whole switch, more than one switch? That's number 1. Number 2, how can we see the content of the flow table? If you want to address those two.
Yeah, certainly. That's also a great question. Part 1, if you want to push to many switches, so far we just have this push to switch script that you basically pass to it as parameter the program and the switch name. So if you have, let's say, 5 P4 switches, they will have the name, let's say S1, S2, S3, S4, S5. You would need to execute that script 5 times. So push to script basic.json S1, push to script basic.json S2, and so on. We did it this way instead of pushing to all the available switches, only because more advanced applications might require different P4 programs in the same topology. One program might be doing maybe some caching, another doing load balancing. They have different data plane descriptions. Part 2, how can we see the content of the flow table? So this is precisely what you would do in the simple switch CLI tool. Okay, now the way we are running it, we are just passing to the standard input the content of this file, which already is there, But you can type in simple switch CLI without anything. You can go to the terminal there. It's like a command line interface where you can simply interact with the switch data plane. And there you have few commands to dump the table entries, or to delete, to insert, to update, and all these different kind of stuff. And this is what we're planning, like the next part of the workshop, which is next week. We're gonna go over this and show example of all these. And the third one is which is the syntax of the rules.cmd. So you can simply like use VI or any editor here, Nano, if you want, to look at this file. So you can see here, I just wrote cat and then this file name, and you can see you have something like table add. You write the block name here, my ingress, the table name, and then the action name, and then the parameters. This is what we're gonna go over next week. But this is, for example, simply to add a certain entry to a certain table. Yeah, no problem.
What you are doing, Elie, is playing the role of a control plane. For example, you are doing a static routing at this point. Or,
yeah,
but that's what a routing protocol would do, or the administrator would do, to push down to the data plane.
Yes, exactly. This is all from the control plane, or if you have like a centralized controller, but you can't do these table adds inside the data plane, inside your P4 program. This has to be done externally, for sure. But yeah, definitely, like, this is something that you might run external algorithms that, like what we do in SDN, right? You might have an algorithm that will create the entries and then push them to flow tables. It's the same idea here. All right. Now step or section number 7, step 1, simply to start the Nano message client to see the log. And it's ready for us now to send packets. Next, we will go to host H2 and start the terminal and execute the receive script. And then on host H1, we will also open the terminal. I think it might be already open here, but you can always open 2 terminals for one host. It's possible. And then we will send 10.0.0.2. So send an IPv4 packet to host H2. And optionally, you can give it a certain payload to be inserted on top of the packet. Okay, so now the packet is sent out of host H1. If we inspect the logs of the switch, so this is in the behavioral model, we can see here that same thing that we saw in the previous lab. Packet entered, the parser executed, and it extracted the Ethernet and the IPv4. How did it know about that? It's basically by inspecting the Ethernet field, the ether type field of the Ethernet header, which is here IPv4, and that's how it knew that the next state would be for IPv4. Okay, and this script that we have here, send.py, is just using Scapy, a Python library, to craft a certain packet. You can tell it, I want, for example, Ethernet with these specific header fields. On top of Ethernet, I want IPv4 with these specific header fields, and so on. You can construct the packet however you want. Okay. Now, we're going to do some modifications just to augment the program to be able to parse IPv6. To do so, it's really simple. All we have to do is go back to our editor, and first we will go to the headers, and then, as we did for the IPv4, we can create a constant here to specify the type for IPv6 now. So const bit 16, and now we're going to call this constant type IPv6, and this is going to be equal to 86DD. Okay. And then we need to add the header definition for IPv6. So we will do it here under this command, and I will type in the code that we see here on the left-hand side. So this is header IPv6 underscore T, and then we have 4 bits for the version. We have 8 for traffic class. We have 20 for the flow label. Again, I'm getting this from how the standard IPv6 header looks like. Okay. And then 16 for the payload length. Payload length. And then we have 8 bits for the next header. We have another 8 bits for hop limit. And we have the addresses, which are these IPv6 addresses, 128 bits. So source address and bit 128 destination address. Obviously, here we could have created a type def for the IPv6, but we just did it with writing the bit and the number of bits in it. Okay. Next, we need to make sure to append the IPv6 header to our header structure, because we are basically planning to use that in our program, so, or to parse it. So this is gonna be IPv6 underscore T, and then IPv6. So we create an instance of the IPv6 tag. Okay, after we do that, we make sure to save, Control S, and then we will implement the parser. So if we go back to the parser.p4, what we have to do here is when we parse the Ethernet, we want to look at the ether type, and based on the ether type, we will go to the IPv6 state, right? Or the parse IPv6. So all we have to do here is simply add. So beside the type IPv4, we will have a type IPv6. And this is going to take us to a state called parse IPv6. Okay. But now we don't have the parse IPv6 state, so we have to implement it in the next step. So state parse IPv6. And here we are extracting the IPv6 header, so header.ipv6, and then we transition to accept. Okay. Do we have a question, Dr. Jorge, before we proceed?
Yes, there is a question. Let me read for you. Eduardo, how is the first packet delivered from the host H1 to the switch? Does the switch has implemented ARP, address resolution protocol, and or ND, neighbor discovery?
Yeah, that's a great observation. Basically, what we did when you use this send.py script, which is basically you know, a SCAPI library on Python, you are crafting the packet, deciding exactly what the source IP, destination IP, source MAC, destination MAC, all these different kind of stuff. And because you are not using a tool like, for example, ping or iperf or any of those that will use the actual stack, and they are standardized, so they're gonna go over the operating system and do that. You don't need here ARP implemented. But on top of that, the current program that we have is written in a way that it will look at the packet and see if it is from port 0, it passes it to port 1. And for port 1, it passes it to port 0. So if the operating system sends an ARP packet, this ARP packet will be eventually sent to the other device, and they will learn the addresses. And that's why if you try to issue a ping command, it still works here. Okay. The other alternative, like let's say if you have a table that matches on the destination IP, this is where you would need to process ARP. Otherwise, you have to hard code the values on the tables of H1 and H2 manually.
And I will just add to this, Elie, that's a great observation, because in a real deployment, we will need the ARP, right? But we're keeping it simple here.
Yeah, definitely.
In this lab library.
Yep, definitely. All right. So now after step 5, we added the parse IPv6. We saved the change, and we have to make sure now that we recompile, and this is because we modified the program. Okay, so we have to reissue the P4C basic. We can use the up arrow to retrieve the previous commands. And then again, we have to repush the output of our compiler to the switch. The password here is password. Okay, so we recompiled and we repushed the updated output of our data plane to the switch as well. Now, let's test this augmented program. So the first thing we have to do is go back to the terminal of the switch. And this is here in the Xterm behavioral model. What we have to do here is we have to stop the logging that we were running before. So you can use Control-C. This is going to interrupt the previous command. And also, we need to terminate the daemon of the switch, which is already running. And we can use something like pkill. This is going to kill the process of whatever name you give it. In our case, simple switch. So we're going to terminate that program, which is the simple switch. Okay. And why we are doing so again, because we recompiled, we have a new data plane description, and we have to reuse that new updated one. Okay, so I will use now the up arrow to restart the simple switch with the updated file, so that we retrieve the previous commands. Okay, this is it. Nothing has changed here. And then step 4, we just press enter to return back to the CLI. We push the rules. I will also use the up arrows here. For this one, the simple switch CLI. So I'm currently executing here. And then start the nano message client. And now what we're going to do is we're going to go to host H1 and send a packet to host H2. But this time, this packet is not an IPv4. This is going to be an IPv6 packet. And we created a script called send IPv6 just to make it a little bit easier, but it's really very easy if you want to play with those sending and receiving scripts, right? Instead of IPv4, you write IPv6. So send underscore IPv6, destination is BBBB and 1, and some payload. So the first thing to notice is that now Scapy is saying that we have an IPv6 address, okay, on top of Ethernet. So we have Ethernet. The type would now point us to the next header, which is IPv6. Now, if we go back to our behavioral model, the BMV2 switch, and see the logs, what we can see here is that, again, the packet was accepted on port 0. The parser started. We started with Ethernet, but because we had this value of IPv6, it knew that the next header is IPv6, and now it took us to the IPv6 parse IPv6 state, which extracted the IPv6 header. Okay, and you can think now that, okay, maybe I want to look at the TCP port or UDP port, and basically all you have to do is extend this parser, select on which field you want to use to determine what the next protocol is. For example, for IPv4, you have protocol field. You can use it and you can infer whether the next header is TCP or UDP or others. And you have to make sure that, of course, you define the headers and you implement that parser well. Now, once this parser works and you are sure that you are parsing these headers, then throughout your program later on, which we will see in the next part of the workshop, in the tables, for example, you will be able to use fields inside those headers. So you can, for example, say, I want to match on the destination IP of the IPv6 header. You can do so. Or you can even do something that is completely different than what you are used to in a regular switch. Maybe you want to parse on the TTL value, or you want to parse on some, I don't know, quality of service fields inside the headers or anything like that. So that's what makes Ipv4 very powerful. You have this opportunity of, or possibility actually of doing processing on fields that are not typically used for a certain activity. You might want to forward based on I don't know, the quality of service field, right? Yeah, and at this point, that's the end of lab 4. Dr. Jorge, is there any question or